All right, thank you so much for having me. So I thought that, it's more fun to kind of have interaction. So you should feel free to please ask me questions while I'm in the middle of the talk. Even if I don't get all the way through, I think that's totally fine. And so if there's something that doesn't make sense or you have a thought or whatever. Okay, so I'm going to talk, my talk has two parts. Part one is the problem, and part two is like, not exactly the solution, but like my current pet theory about the solution, roughly. Okay, so that's how I'm organizing it. So I'm going to talk about the problem. To do that, it's useful to have a little bit of this old school background at this point that I think puts things in perspective, which was basically the idea of trying to build neural network models of the brain without like directly fitting to the brain. Okay, I used to call this task optimization, but I think it's a little bit of a misnomer. Basically, it's like you optimize it for some task. Okay, in this case, I'm imagining 1,000-way ImageNet categorization, but it can be other things, like we'll get to in the part that in this first part of the talk, that you wouldn't necessarily think of as tasks, but they're at least just objectives. So you can think of what Ilker was talking about as like a different objective. Maybe it's the same architecture, maybe it's the same learning rule, maybe it's similar data, but in any case, the objective is different. In this case, the objective can be categorization. Doesn't matter. It's optimized for something that you think is kind of the evolutionary pressure on the system, and then you can compare it to brain data. Okay, so this was kind of the old school thing that we had been doing for a while, and it was useful at helping us and many others make models of different parts of human brain and also other parts of non-human animal brains. So like, for example, vision and audition, but also, like motor system, olfaction, human language, from many researchers, far from just our group. But the idea is, you optimize the neural network to do something and then you compare its internals. And if the model has done something that previously behaviorally was hard to do with the model, it's probably a good bet that will make it more brain-like for the areas of the brain that do those tasks. Okay, it sounds almost tautological. I mean, it is almost tautological. It's just the idea behind that is simply that neurons are at least somewhat constrained by behavior, and that behavior might be inverting the generative model of the scene. Okay, I think that's a decent hypothesis for what the type of behavior is. But one of the things that really bothered me quite some time ago, and when I was starting my lab, was one of the things I thought would take a really long time to make any progress on, but it was really bothersome, was the fact that we were building models at the time that were supervised, and that you did a task with 1,000 category labels or something like that, different categories and 1,000 labels per category, and it was just something that these animals just didn't do, right? So while the theory was kind of cool in some ways, I think that there was this big problem that arose, which was how do you learn this in a reasonable way, right? Because real visual experiences like this, and this is from a data set from Linda Smith's group, among others, and obviously you don't get labels for everything, and it's not like every time you see a plate, the parent says plate or something, right? So it's not like there's necessarily a good label for everything. And this was really brought home to me. I was starting in Stanford, and Mike Frank, my colleague at Stanford, told me about this data set that he was collecting. This was back in 2015 in the CogSci meeting. Finally, it got published in 2021, but the data set existed for a while. And what this was this wonderful thing where they had basically mounted head cams on kids and measured their data. And he said, well, so can you help us with this data? Right? This they had 3 infants, 6 to 32 ages a month, head-mounted camera, mono video audio channels, 2 hours a week. So he was like, so how would you use this data set to learn a representation? I was like, I have no idea, because there's no labels, right? What am I going to do with this data? And this basically seemed to me to be a grand challenge, okay? Of course, the answer had to be some form of unsupervised learning or self-supervised learning. In some sense, that was clear. But the problem was, how do you actually do that, right? And this was a thing that bothered me for a while, and it was certainly something that had been bothering other people for quite some time as well. So unsupervised learning had this kind of long history. For a long time, it kind of didn't work very well, okay? But then kind of around 2018, 2019, things started to change. There's this new family of methods called deep contrastive embeddings that arose, okay? And there's a long history of how they came from different ideas, and I'm not going to give you the whole history of how deep contrastive embeddings came about, but I'll just briefly mention that one of the players in this was my former student, Cheng-Xu Zhuang, who went on to MIT and has now moved on to even bigger and better things, but he did quite a bit of work at like establishing that you could use contrastive embeddings to learn visual representations and use that as a model of the mind or the brain, at least the visual system. So, contrastive embeddings it's a big topic. I'm going to just briefly tell you a little bit about how it works. This is one of the algorithms that Cheng-Xu developed. Basically, instead of optimizing for now, okay, it's the same architecture, just like Ilker said, the architecture hasn't changed, maybe the data hasn't even changed, okay? What's changing here is the objective function, right? So now the objective function isn't invert the generative model of the scene, or at least not explicitly, okay? Instead, and it's definitely not categorization, right? In this case, it's something a little different. In this case, it's something like, you move your head around an image, and that gives you different crops of the image, like I'm doing here. And then you optimize your parameters, not to do categorization or whatever, but just to put the things that are crops close together in the embedding space that it's going into, and to move apart stuff that's not generated that way, okay? That's the basic concept behind contrastive learning. And there's many twists and turns about how that works, and in the local aggregation algorithm that Cheng-Xu built, it's a little more complicated than that, because in that case you have things that are like close neighbors and background neighbors, and you treat them differently. You basically push things that look like they should be really close and clustered together, things that are close but not clustered further apart, and then you do nothing with the really far away neighbors. Kind of an inverted U-shape function. Anyway, the point is that there's this whole class of contrastive learning algorithms that try to do something like this. And when you train them, we start out with some kind of structure that looks kind of random, okay? And then over the course of training, even though there's no labels, things that are kind of like, I don't know, multi-scale, category-ish like embeddings of things arise. Each dot here being a different stimulus. Question?
I think I don't understand the paradigm. When you're saying crop, you're saying like zooming in on a relevant thing, or do you mean something else?
It could be zooming in. Yeah, it could be even in.
So that has to be done by hand? Or?
Well, no. I mean, so you said something that was really interesting, which was zooming in on a relevant thing. In principle, you could imagine a learnable policy that would define what relevant meant. In this kind of case, it's really dumber. It's just random cropping and like whatever your data, whatever your images are. But I mentioned like moving your head because I think that's something like it's like the natural physical implementation of how the policy that would allow you to generate that so-called those positive samples of the same thing, the thing the contrastive algorithm wants to call the same. Does that make sense? Okay, yeah. So okay, at the time this was doing pretty well, this algorithm. I think that like for us, when you could get a self-supervised thing to be better on ImageNet, to be able to transfer to a linear probe better than something trained directly on ImageNet, albeit with a smaller amount of data, that was a big milestone. And you can see that these algorithms were decent at making predictions of things. Not just categorization in terms of categorization tasks, but like other object type tasks like object position or size. Here, black is supervised and red is these contrastive algorithms. Of course, supervising on classic categories is always better with the same amount of data than self-supervised. Although you can push these numbers up by having a lot more data, which you can do because you don't need labels. Okay. But in any case, even on other tasks, they can be better. So it's kind of saying, from a performance perspective, you have this sort of fairly task-generic representation. Actually, there are some people who have said, although I don't know if this is totally true, and I don't know if Ilker would agree, that contrastive learning inverts aspects of the generative model. Have you heard that? Read that paper? Yeah, there's a paper about that. I don't know whether that's totally true. It's certainly intuitive that it might do that to some extent. These kind of self-supervision is not trying to solve any particular task. It's trying to figure out what is the structure of same different distinctions that exist in the data. Okay. Now, for us at the time, right, we were, this was back in 2020 or so. We were interested. Okay, how well do these things match neural data? Okay. And so Cheng-Xu did a really tour de force work on this. And what he found basically was that these contrastive algorithms, including especially several of them, were particularly good models of neural response properties in the brain, kind of like old models had been that were supervised. They were a little better, maybe, not that different, but we're getting there, and in sort of in this case, kind of closer to having a quantitatively accurate unsupervised model of this higher brain area, which was for us like something that, if you would ask me in 2017 how long it would take for us to do this, I would have been concerned that we might not have it 10 years later. But it was actually pretty fast once people had figured out this principle of contrastiveness, okay? And similar to kind of the ideas that Ilker was talking about a little earlier, like we were interested in the different correspondences of the areas. So, like we had seen with categorization-based networks, these unsupervised things, contrastive ones had this kind of anatomical consistency in that early areas of the model look kind of more like V1 and intermediate look more like V2 or V4, and then higher layers look more like IT from a neural response prediction point of view, okay? And then since then, many more self-supervised, contrastive algorithms have been proposed, and many of them are good and better, and like people worked on this for a while. Okay, I think this is like kind of climaxed in what some of you may know Dino V2. For those who don't know it, it's a version of a kind of a contrastive like learning. It's one of the best representation learning things that are there. It's kind of in this flavor. Question.
How did they do with adversarial examples?
Not much different than categorization-based ones. So that was something that I think always felt like it would probably happen and then just totally didn't happen, which was that it was totally not the case that the self-supervised things were like that much more robust to adversarial examples than categorization supervised ones. And that was really unintuitive. It was sort of intuitive that it had to be the other way, and it just totally turned out not to be true. So far as I know still, it is really basically the case that the only way to get pretty good robustness is to make it robust by doing adversarially robust training, okay? And it is actually true, as a side note, work from Jim DiCarlo and others has shown that the adversarially robust trained models are actually good models, better models of neural response prediction than the ones that are not adversarially robustly trained. Adversarial training is probably not a biological operation in the most obvious way. But anyway, that's a mystery, and I don't know the answer to that. But it's yeah, okay. So I wish what I'm going to say is not going to tell you any insight on that. Yeah, okay. So, okay, as I say, more things have been proposed, but one of the nice things that Chung-Hsu realized you could do was apply the contrastive idea to video. And he built this nice contrastive video learning algorithm that had a kind of a static stream that processed images and the dynamic stream that processed video. It's essentially 3D conv. And what he found was, okay, look, this did a decent job of predicting, doing like computer vision tasks. So this was a CVPR paper. But the key thing that we were really interested in it for was that we could apply it to the video that came off of the baby data, right? And this was really interesting. It was a harder problem in many ways, learning from ImageNet, because it's online versus buffered. It has many fewer distinct examples. So like instead of 1,000 cups, you get to see the same 3 cups over and over again from weird angles or whatever it is. But anyway, the point was you could stick that baby cam data into the algorithm, right? And it turned out that when you did that, you got like decent results, meaning that you could get good, decently predictive models of V1, V4 IT out of a model that was trained on the video data, okay? And that was nice because it meant that you didn't actually have to stick with, like ImageNet, and you could actually run it in like real world, situations. And there was a small advantage to using video compared to still frames. Oh, question.
So do you have any intuition about why this untrained network is doing so well on the V4 dataset?
As opposed to, well, it works about the same on V1 and V4 and IT.
Yeah, V1 and V4, yeah.
Why does it work as opposed to failing where?
Like in IT, for example, in IT, it doesn't do as well as like 0.4, for.
Oh, do you mean why are these numbers lower?
Yeah, just for the untrained ones, right? If you look at V1 and V4, the untrained ones actually is doing pretty well. It's about
okay.
0.7, yeah.
Yeah. Let me just try to make sure I understand your question. Are you trying to understand why this number is low compared to this number, or why?
Yeah, it's a little bit both. Yeah, just
okay.
For IT, you see there is a big contrast between the trained network and untrained one. But for
okay, I think you think about it this way: the untrained networks are still very good networks. They're good architectures, right? If you took it, you shouldn't think of untrained network as being a random network. A random network, a randomly chosen neural network, is terrible at this. But a good architecture with randomly chosen filters is actually a pretty decent transfer function, right? So actually in my very earliest work on this, I didn't do any training of the filters at all. They're all random filters. and you were just looking at different architectures, and a lot of the ability to do decently of any of these models, a lot of the ability of any of these models, any model that I'm aware of right now, to do like half or more of the explained variance of neural data comes from the architecture being decent. And you could put in random filters. Of course, you can't put in 0 filters. That would kill the model. But randomly chosen filters, the architecture still shines through.
So if I understand correctly, you're saying the architecture, Sam. So if you just use an untrained 2-layer feed-forward network, then the number for that untrained network will be much lower compared to the untrained version you have here. So you have carefully
If you pick a random feed-forward network with like random parameters, architectural parameters, the others are much worse. So like if you go back to my original work, you see that like the randomly chosen architectures suck, okay? But like half or more of the value in IT comes from, even in IT, this is way higher than chance. Way higher than chance. You know, chance, a randomly chosen network is like here, okay? So, you know, and it's more, the higher you go up, the more, the worse, the less you get bought from the architecture, but still you get some meaningful. So, you know, I don't think of, yeah, this is an important question because you can actually look at like other metrics of the V1 and V4 models. So for example, if you take the V1 model, it has, you know, it has like Gabors, which you wouldn't see just by this calculation. This is a linear calculation. So, you know, Gabors are not linear invariants. And so, you know, like there are probably other metrics that expose the difference between having random filters and not. And yet it is still true that actually I think it's quite reasonable that the correct architecture, you know, the correct, like let me put it this way, like differences between VGG and like AlexNet and ResNet 18 or whatever aside, really small, terrible ConvNet architectures are going to be terrible at this. And you know, the more that you get close to something like AlexNet with the right filter sizes and so forth, the better it gets. So, yeah, okay. So, nonetheless, there's still a gap, right? And actually, I think that like one of the things that I found really surprising was that actually training on real world video is actually not better than training on ImageNet when it comes to making neural models, and there's still a small gap there. So, you know, okay, overall, it's like maybe 3/4 of class is 3/4 of the way full or something like that. But for me, what I'm saying is you get to beginning to have something like a candidate model of visual development from this. And just to summarize this part, you know, contrastive unsupervised approaches finally largely made up that supervision gap in performance on neural fits when trained on developmentally inappropriate data sets such as ImageNet, and then they were kind of okay in real data streams, okay? Not perfectly, but let's say kind of okay. And I'm gonna just briefly mention something else that has happened in my group because I'm happy with it, but not because it's actually topical, which is that kind of using, it's only slightly topical, which is basically that using the self-supervised models that I just showed you before, we then built topography into the models, and that was a big advance, I think, because it allowed us to start explaining things like, you know, pinwheel, you know, structures in V1, and then like, you know, face patches and other patches in higher areas, such that you kind of have this overall kind of topographical self-supervised network as being a kind of decent description of the system. And then that's basically the TLDR is we can integrate 2D cortical topography, and that helps improve the match of features to the brain, okay? But that's especially good with the self-supervised models. But like, I wasn't sure whether I should introduce this here or later, but I just wanted to remind you of the bitter lesson, which is the idea that you should not make things too complicated, and as much as possible, use large but simple models and good data, and the architectures and loss functions don't matter all that much. And I'm going to generalize that to call the Sutton-Efros conjecture. Alosha Efros is a computer vision scientist at Berkeley, and he kind of has this view in vision in particular and has been quite productive following that. So the reason I put that here is because, like, let's say we wanted to do better, right? Actually, one of the things I was a little disappointed about was that actually with our contrastive models, we weren't actually better at predicting neural responses that much anyway than the categorization-based ones. And so like there was always this question of how we were going to do better. And you know, was it going to be through building in some special structure, or was it going to be how are we going to push the data if we're going to take the bitter lesson approach? How are you going to push the data and like, you know, like simplicity further to, I mean, it's kind of what we had tried to do thus far. How are we going to push this further? And how are we going to make up the fact that, you know, these models are quite imperfect, and especially that they were not especially good at existing developmentally appropriate data sets. Or they were okay, as I said, but they were not perfect there, right? And a reminder why this was important is that like when you're actually learning from real world data, it's a different problem than when you have like simple data sets that have been like cleaned and organized for you from a computer vision perspective, right? And so, you know, in thinking about this, there are these two hypotheses. One is that the algorithms were insufficient, okay? And the other is that the data are insufficient, right? So what would that mean? Well, you know, it would be like if you had all the data that you needed, could you learn a representation that worked, right? And up until very recently, we really have not had enough data to know. Like the SACAM data set, remember, that was 2 hours a week. That's a 50th roughly of what you'd have to be able to say that you had like a full like representation, you know, a full set of the data. And so at least to be able to make extrapolations, you probably have to have a little more data than that. And so for this period, sort of between the contrastive algorithms developing and recently, I felt a little bit stuck in the sense that we knew what hypothesis we wanted to evaluate, but didn't have the data quite to do it. And so one of the things that was happening at this time, and this was a project that I was, you know, like very much trying to support financially and also through like, at least meant morally, although the actual work was done here by Bria Long and Mike Frank, was to the BabyCam project, plus project, or we've called it different things. Now it's called BabyView. But basically the idea was to at least get one child's year worth of data. I mean, ideally we would have liked to have 10 years. Right now we've got kind of roughly like 1 year worth of data. This, as I say, this project was really driven by Bria Long, who has just moved down to UCSD to start her own lab. And Bria really coordinated this data collection and quality and work project entirely. And basically, the difficult thing here was building a device and then organizing the families to use it and capture this data. And that was a lot of work. And so, you know, Bria is a better person to tell that story. But the key thing was simply that we could get this data. And it turned out that the new data was better for like running standard computer vision algorithms on, better than the old data that I mentioned earlier. And finally, hopefully we have indeed crossed the threshold of 1,000 hours, and this will hopefully be released quite soon. Okay, so you can use it yourself and try out training algorithms on at least the first version of BabyView. Hopefully we will have more than 4,000 hours by September 25. But anyway, the point was, okay, like sort of hot off the press, roughly-ish hot off the press, results at this point on this data set I think are very motivating in a certain sense. So, okay, look, here's our x-axis is how much data, hours of data, and y-axis is performance of a network trained in a self-supervised manner on this data, and then tested on some task like categorization through a linear probe. We can talk about what the way that it's probed, but anyway, it's a linear probe. So on this task is a task for reference that humans are about 95% accurate at. If you take the state-of-the-art Dino V2 self-supervised contrastive algorithm and you train it at 500 hours of data, it's 75.2%. And then at 1,000 hours of data, it's 75.4%. So actually, you know, the extrapolation suggests that with about 11,000 years of data, we're going to get to human performance if the error bars in our extrapolation are to be believed. And then the situation is a bit worse with other tasks like depth estimation or basic semantic segmentation. Okay. Just to put it in perspective, it seems to me like we have enough data at this point to keep our extrapolation error bars small enough that we can say that probably some kind of newish hypothesis is needed. It's not just a matter of running Dino V2 or whatever standard contrastive algorithm you want to use on the right amount, the amount of data that humans can have. It's not enough to just perhaps have more data, right? This is like the simple, like Sutton hypothesis is that you could just use whatever, doesn't matter what the algorithm is, just put a lot of data through, it'll be fine. Okay, I think that's probably not true, okay? Maybe you need other kinds of data, like other modalities, like audio-visual. That's always a possibility, although, you know, other people who are not sighted or hearing learn how to do the other thing quite well. So I'm always a little skeptical of this hypothesis. Maybe you need language, although monkeys seem to learn how to see fine. So I'm not sure of that one. Maybe you need embodiment. I think that that's a possibility. But of course, there's always the possibility that actually what you really need is some other kind of algorithm that has some other deep idea in it, okay, for whatever that may be, okay? So this is another way of saying, okay, like I told you some nice stuff about contrastive algorithms doing decently well, but like basically what I'm telling you is that there is a problem with them, okay? At least so far as we can measure, okay? And so if part one was like the problem, part two is gonna be like my pet idea about how to deal with this problem that like, you know, we did so well with the contrastive algorithms, but we couldn't push them further than that, and that really seemed to like, you know, as I say, suggest a substantial problem to be solved. So before I go into part two though, there's gotta be at least one question that I can get somebody to ask, and, okay.
So I understand that most of the time people are learning through unsupervised learning, but at least in human experience, there is quite a lot of supervised. Do you think this could help adding some supervised learning on top?
Yeah, no, I think that's good. So this is my chance to use these like slides. So I'm gonna just put them out because I did some work on them. I don't think it's a full answer to what you're saying, but of course we were interested in semi-supervised learning as well because humans do get something that somewhat seems like a label. So actually, Changshu showed that you could use contrastive algorithms, Changshu and others also, show that you can basically use the same metaphor underlying the contrastive algorithm to get a semi-supervised algorithm that takes a little bit of labeling. So that's basically like, you know, if the contrastive algorithm loss function is this, then like you can basically make a semi-supervised learning algorithm from that by basically propagating from a few labels using basically them as positive samples, and you can figure out how to get the negative samples sort of similarly, and that turns out to be a pretty nice semi-supervised learning algorithm. And in fact, just to make a long story short, if you want to, what they are particularly good at, and you can compare this to data from human and monkey behavior, is the ability to predict neural, like not just neural response patterns, but behavioral answers. So like this kind of semi-supervised thing are nearly as good as the categorization algorithms at predicting categorization error patterns, okay? Now that's just, I'm just showing you some work I did, okay, which was fine, but actually I don't think it totally like resolves the point that like, at this point, given what I've shown you just before, which is that they're like even the best self-supervised algorithms are not kind of getting all the way there. It's not like the semi-supervised algorithms get us all the way there either in terms of, certainly not in terms of many different types of behavioral tasks. So I don't have that result to show you here, but I'll just assert that the semi-supervision doesn't rescue us, okay? As much as I wish it did, in fact, and then, you know, of course we did some work on semi-supervision, nonetheless it doesn't rescue us all the way. Yeah, question?
So I don't know too much about vision models, so you can just ignore it if it doesn't make sense. I had this rough impression that often the kind of self-supervised training was trying to predict certain patches from other patches. And if that's the case, how does that compare to this contractive?
Yeah. There's basically two types of self-supervised learning out there, okay? One, which is contrastive, and the other is predictive, okay? And I think you're thinking of the predictive kind when you're mentioning the patch stuff. Let me do the other half, and then that won't totally answer your question, but I'll come back to your question.
Okay, thanks.
Okay, yeah, question.
I'm not entirely sure this question is relevant, but on the slide where you compare the I'm not entirely sure this question is relevant, but on the slide where you compare the performance of the model on gradually more amounts of data from the Baby View project.
Yeah.
I don't know if this is relevant, but what is the performance of a child onset task? Is the model performance?
Well, you know, it's a good question. It's very hard to get child performance on this task. Like, so I really don't know. What you can do is measure adults. And you can ask whether or not the algorithm that you were hoping was a developmentally generic algorithm would give you adult performance. And it doesn't, okay?
So is it possible that it's just getting child performance? I mean, I don't know very much about developmental.
But if that were, okay, now it's possible, right? But if that were true, what that would basically say is there is some thing that happens after childhood that is special in the mind of the adult that allows it to do better. And that's so I guess it's possible. There's like two, I guess you could go down this tree. Either the algorithm should be unified and should get to adult performance with an adult amount of data, and it doesn't. Or like, yes, this algorithm is right, but it only holds for children up until, I don't know, 5 years or something, and then suddenly it switches to something else. That's possible, but that seems more complicated. So my suspicion would be that because the algorithm doesn't get to adult performance with an adult amount of data, it's probably not a good model of children either, even though, of course, for some age, the algorithm's performance will match that child's performance, because at 0, the child isn't doing very well, right? So, like, I don't think it's a good model of just the child.
So it doesn't matter that. So it basically doesn't matter what specifically the data is taken from.
Well, okay, no, of course it does, and it would be really very nice to compare any of these algorithms to child data. It's just that child data is very hard to come by. So, like very smart, very, very hardworking scientists like Cameron Ellis, newly joined us at Stanford, are trying to measure things like that, and he and others. So ideally, we would make a comparison to child behavior. It's just that's hard. So I'm sort of punting your question, but I still think we know that the algorithm isn't right. Yeah.
Just a really quick question. So what does the learning curve look like below 500? Does it, how much data do you
It's
to
pretty
saturate
fast.
data?
It saturates quite fast, actually. I'm sorry I don't have a picture of that, but yeah. So I don't know. Like you get pretty close to the 1,000-hour amount at like 100 hours. Yeah. So it's certainly learning something, right? It's not learning nothing, and it does do it quite fast. It's just I mean, maybe there's something we're doing wrong here. That if we did it just quite a little different way, suddenly it would work fine. But we haven't figured that out. Yeah.
I was just going to ask that, like, just to better understand this plot. Is it, dynamic version 2 isn't making as good of the data going from 500 to 10,000? I mean,
yeah, it does. It does great from 0 to like 100, and then or 0 to 75 hours. It learns a lot, and then it kind of tails off very, very quickly. Right now, maybe we're doing something wrong. Okay, I wish I knew what that was if that were true, but so far not. Yeah.
I don't know these contrastive models. Does it mean different from background?
Yeah, it basically means you have some notion of what counts as the same and some notion of what counts as different in a very bootstrappy way. You basically start with like almost no information of what counts as the same versus different, but you add a little bit, like by saying crops are the same, and then things that I saw earlier were different. Okay, that's just one way to do it. And then you basically, the way the algorithms work, they basically bootstrap on that concept, and by virtue of bootstrapping on that very minor apparent amount of information about what counts as same versus different, they do seem to learn like a lot of same different features that are really good for differentiating in different semantic quantities, basically. Yeah, maybe by virtue of the fact that they partially invert the generative model, possibly.
The other question is, in your presentation, the vision is a rectangular array.
Yeah.
Right? But eyes don't have, rectangular arrangements. They have, curves that you can see.
Yeah.
Did anybody investigate why?
Lots of people have invested. Well, certainly it's very expensive to have the cone density that you have toward the center of the, sort of foveal or parafoveal visual area. So, it's much easier, much less expensive to have peripheral vision and central vision. Oh, yeah, well, I mean, probably it's because of the density changes, so they're not arranged in a grid. Lots of people have tried installing, like, log polar transform, for example, way of describing the actual density of visual systems, and it makes a little bit of a difference, but it's really, I think it would be extremely unlikely to say that that would be like the other kind of algorithm. I don't think that that's, just to put that sort of in perspective, I don't think that like a realistic model of like the eye is going to solve this problem. That's my current understanding. Yeah. Okay. So, all right. So now let's go to this other part 2, this kind of possible solution concept. One of the things that is sort of very notable in visual systems neuroscience, and also actually in old school computer vision, is the fact that there was so much attention paid to visual intermediates. Okay, so what are visual intermediates? They are like the things that you see in pictures of, like old school pictures of the visual system, where you start kind of with like, I don't know, center surround stuff in early visual areas, and then you kind of get edges, and then you maybe put them together into corners, and then you have these kind of curvy shapes, and then finally you get to like, I don't know, proto-concepts or something like this, right? So this is the kind of picture I think people in visual systems neuroscience think of when they think of vision intermediates. And certainly, they've been very useful in computer vision as well. So I'm making a list here. There's like, I won't read them all, but you can read them. There's a lot of these named visual intermediates that people have thought about both from a vision science perspective and then also in computer vision, at least old school computer vision where people used to do like, bespoke systems, right? And many of them are sort of like, you can sort of put them in roughly something like a hierarchy. Like maybe optical flow is kind of close to the early system. You don't need a lot of structure to do optical flow. But then like if you want to like capture like a 2.5D sketch or a 3D volume or a 3D mesh or whatever, you need that somehow higher in the hierarchy, right? That concept probably makes at least some intuitive sense. So I'm going to talk about two things, okay? One is, where do these visual intermediates come from? Okay, like even if you think they're not useful or it's like anti-Sutton to like be thinking about the structure of these intermediates, anti-bit or lesson, nonetheless, people can do them and they do seem to name them. So it's a good question where they come from. Okay, especially since many of them would be very hard to label. Okay, it's like hard to get labeled data for 3D meshes or something. And I think that's part of the difficulty with doing, generic, like inverting the generative model. And then of course, you might wonder, are they useful for AI, right? Like if you could figure out these things and you had access to all these different intermediates and you could invert, in many ways, these things are like inverting aspects of the generative model of the scene. If you can come up with them, do they actually help you build a better model? Okay, and I'm gonna talk about that one a little bit, but not too much. I'm gonna mostly focus on the first one as kind of a route, possible route towards thinking about how to build better algorithms, okay? Early, developmental, science, cognitive science has shown that kids have pretty good physical intuition. These are famous results from Liz Spelke, among others. And for me, that was a very motivating thing. I think it's motivating for a lot of us because it's sort of like, where does that come from? How does physical intuition arise? And I think it's very natural to think, okay, if you want to use intermediates, then physical intuition would probably be helpful. Like, for example, here's kind of like a conceptual ladder that you might use to climb towards physical intuition, and you use these various intermediates along the way, and it feels like you've learned something intuitive about what's happening. So one is, you might start with the ability to, if you could, extract optical flow from video. And then from that, you might build segments, like basically stuff that moves together. I'll come back to that point. But in any case, you can imagine that you figure out the segments from optical flow, which then, if you knew the segments in different situations, you might be able to get 2.5D or 3D shape from that, which could be then used to understand scene graphs, which could then allow you to have physical intuition. This is pretty similar to the idea that actually you want to invert the generative model of the scene in some way. It's just a particular pathway towards doing that. Okay, and I'm going to call this something like a Spelke-Marr synthesis, a kind of synthesis of ideas from Liz Spelke and the great computational neuroscientist David Marr, who talked about a lot of these intermediates as part of his work in computer vision and also in thinking about computational neuroscience. So if you're a devotee of modern neural networks and the Sutton-Efros hypothesis, you should be quite skeptical of this idea, because this feels quite bespoke. Okay? The third person on that is Tommy Poggio. In fact, David Marr is the one in the background, and this one is Tommy Poggio. Yeah, so I like that picture because it's got them both in there. So, yes. Okay, so let's talk about this hypothesis for a little bit, okay? And in particular, we'll talk about the first two. So imagine you are looking at the scene. This is a scene from a robotics data set. And you want to be able to segment the objects in it in this kind of category agnostic way, where you don't need to know the category of the object before you figure out the segment. Related to the thing that Ilker showed earlier, which is like you can still get the shape of something even if you don't know what its semantic category is. Okay, so right, that's a natural task to want to do, to be able to figure out what the segments are, not by looking at the motion, but by looking at the static scene, which could then allow you to take actions. Okay, and so here's a basic idea from developmental cognitive science that could, if you implemented it, might help you, right? This was basically a hypothesis that we had, and this is, you sort of take that idea and just make it into an algorithm, right? So I'm gonna define a Spelke object as a collection of stuff that always moves together under the application of everyday physical actions. Okay, it's only one kind of object notion, but it's one of them. And so, this is kind of the one that you might think come from, at least to some extent, from the work that Liz Spelke and others did on objects. And there's an obvious idea that comes out of this, which is step one, extract optical flow from video. Step 2, threshold the optical flow to get object borders. And step 3, train a static segmenter from the teacher signal in step 2. Okay? This is a very natural way, if you know how to get optical flow, to probably try to get objects that move together, the Spelke object notion. And indeed, this was something that worked to some extent, worked decently well, and work that we did with Honglin Chen led, but also advised by Josh Tannenbaum and Jiajun Wu. And basically, what we were able to do is get decent self-supervised segmentation out of that approach. But one of the things that was really bugging us about it was that thresholding optical flow does not work in many real-world situations. This is basically the Sutton hypothesis, the bitter lesson biting us, because it's like you have a concept in your mind of a clean algorithm, and then you try it, and it works to some extent, but actually there's a lot of holes. So for example, here's a situation where you have a bunch of sheep, and in this case, thresholding optical flow does not separate objects, okay, because they're all moving together. And here's a situation where you have a deformable object, and so thresholding optical flow is quite problematic for figuring out the segmentation in this example as well. Okay, so we needed to do something else, and I think that in responding to this, we were able to come up with a hypothesis that I think has the potential to give us ability to thread the needle of not being too bespoke, but still allowing us to understand where a lot of these intermediates come from. Okay, so this hypothesis is this unifying aspects of machine vision with counterfactual world modeling. Okay, and so a lot of folks in my group have been thinking about this, and I'm happy to highlight these folks here. I'm happy to tell you about them, but Honglin, Rahul, Clement Wanhee, Dan Baer, Kevin Feigelis, they've all contributed here. So in telling you about this, I'm going to remind you of a notion that came out of, really out of thinking about inference, which is Judea Pearl's notion of the ladder of causation. So in level 1 of the notion of ladder of causation is association. That's the notion that you want to be able to understand what the ground truth associations between pairs of events are. So in this case, estimate the probability of y given x, where y is one event and x is another. Okay? An intervention is the second level. It's the prediction of what happens if you specifically break out of the distribution to make an assertion about what something should do. So this is the probability of a given event, y, given that you've done something specific together with some other background data. Okay? And then finally, counterfactual, which is basically an analysis of what causes x by comparing interventions to the ground truth. Okay? So just, if you've heard of this, this will make sense to you. If you haven't, this is probably too fast. But in any case, there's this notion of how you would compare various forms of basically conditional estimation to be able to extract understanding of what's happening in a system. And that's a very generic thing. I'm going to now make it fairly explicit. Okay, so now back to your patch notion. Okay, the masked autoencoder is an algorithm that basically gives me, you take the image, you patchify it, and then you mask a bunch of the patches, and then you force yourself to try to predict all the remaining patches, okay? And this is basically the other style of self-supervised learning. This is predictive now rather than contrastive, okay? And that turned out to be decent, although probably not as performant as contrastive in many circumstances, but it was actually pretty decent and very simple. People have applied this notion to forward prediction in video as well. I'm gonna tell you about an idea that comes out of that framework that I think has the ability to frame how you would extract a lot of different visual intermediates. So imagine you learn a prediction algorithm now that goes from pairs of frames, okay, to each other. And in particular, a mask policy where you give me all of the data about frame 0 out of a pair, and then a tiny little bit of the data about frame 1, okay? And then your prediction problem is to predict all of frame 1. So here it's like frame 0 is this person riding a horse. I give you a little bit of few patches of frame 1, like 1% of it, and then I got to predict what happens next. Okay, that's a prediction problem. It's a specific form of masked prediction problem. Okay, imagine that these frames are fairly close to each other, but kind of along on the order of a couple hundred milliseconds. So like what you might imagine one sweep of the visual system to do. Okay, so this choice of masking policy, to the extent you can train a model that does this, causes factoring of motion from appearance. Okay, you might be wondering, hey, why would it do that? Okay, but it's really easy to see. If it can train at all, it's got to do that because if you can figure out what the appearance of frame 2 looks like, or the second frame, frame 1, it's got to come from appearance information in frame 0 because it sure as heck isn't coming from here, frame, be a second frame, right? Your few patches there. And second, but of course, object transform information has to come from frame 1, because else you wouldn't know how it moved, right? So that function, to the extent it works, has to learn how to separate those two sources of information and pack them into different tokens. The appearance information to the token in frame 0, and the motion into these few number of tokens that you give in frame 1, and then the predictor has to effectively learn how to apply the transform to each object. Again, it turns out that you can train such an algorithm very well. You can reduce the loss on like YouTube video, basically. And what comes out of that is a pretty powerful predictive model, okay? So I'm now gonna show you that temporal factoring kind of in practice. Okay, so imagine I give you 2 frames, time t and time t plus delta, the horse has moved forward. If I give you the initial frame and I give you only a little bit of the second one or 2 points, what will happen is actually the horse is quite blurry. That's because you don't know how far it's going to move. But the background is sharp because it has come into focus. Basically, the system has figured out what the background panning of the camera was from that one piece of information. And then as you add a few other pieces of information, you can sharpen up the whole picture by telling us a little bit about where the objects have moved. Okay? Question?
Does it matter where that single pixel is? Like if you put the single pixel on the horse, would it still do background?
No, it won't. In fact, it does matter where it is. It doesn't matter during training. You can train it with random. But once you have the trained algorithm, then you can have this interesting question of what policy you would need to use to figure out which piece of information is needed to sharpen up which part. And that's exactly the notion of how you would, something that sharpens it up is exactly the policy that extracts where the objects are. I'll come back to that, so there's a question.
This is super interesting. Like in the way, the added pixels are impacting blurriness or uncertainty in the predictions. I mean, one would think as soon as you showed me some patch of the guy riding the horse, I should know a little more about the horse.
Well, you do know a little bit more about the horse. It's just that the horse could have moved its legs in like,
it seems that
many different ways.
the body of the horse seems just as blurry right across.
Maybe that's like an error of this particular example, but in general, that's quite true. Yeah. So the really blurry part here are the legs. I think it's partly due to the I don't know. The body of the horse is much sharper, indeed, and I'll prove that to you in a second by a second thing that you can do with it. Okay. So, but just to put that in perspective, what we have here is shown that you can basically do with level 1. This is associative learning. It's basically the notion of learning how to predict from some patches in frame 2 in the first frame what the rest of the thing looks like. Okay, it's learned, the model has learned that conditional generation function, okay? But of course you can do things that are interventional, okay? You don't just have to stick with the original pair of images. So maybe it had to do with the fact that the input resolution was just low in that image. Here's an example of an image, same model. This is a high resolution image from my iPhone in my kitchen. Okay, and so for example, what you can decide to do is hold the bowl still by not moving that patch while moving the banana a little bit by moving one patch on the banana. So if you stick this counterfactual into that model, so you basically have this whole image plus these 2 counterfactual patches, or intervened patches anyway, that's the do operator, okay? Then what we have is that the bowl will not move, but the banana will, okay? Now, of course, this is an L2 model, so there's a little bit of blurring in the background. Okay, if you do this with autoregressive model, you can make it really sharp. But anyway, it's good enough to see this in an L2 model. Okay, so the banana has moved, and the bowl has not. Okay, so that's the idea that you can actually do an intervention on top of this model to make counterfactual predictions. So basically, whenever you have a patch-based structure where the patches basically are like different pieces, this kind of model is effectively learning that generative function, okay? And here's just a bunch of examples, and I think some of them are interesting. Like if you want to pitch the bowl upward, then that's like saying I move one of these, this one down and this one up, and then that gets completed as a sort of out of plane rotation, okay? Okay, but finally, okay, I've mentioned 2 things. I've mentioned first the association and then this interventional notion. Now I'm going to tell you about the counterfactuals themselves and why they're useful. So in particular, it's sort of like an analysis or a little program for understanding what causes what, okay? So let me make that clear. Let's start with a really simple counterfactual, a tracer. This is basically an appearance counterfactual. So here's a ground truth image. And here's this perturbed image that I'm going to show you. So this is an image where I've taken the original image, okay, and then I added 3 pieces. I added 3 little squares, basically. A red square on the horse, a green square on the sky, and then a blue square on that location on the background. And that's an intervention, like I showed you before. Okay, here are the 3 little pieces where we've done intervention. So now, I'm going to talk to you about the idea of running the forward prediction in the clean version versus the counterfactual version, okay? So the clean version gives you the clean prediction, and the counterfactual version gives you the counterfactual prediction. Or I don't know if you want to call it counterfactual or not, but anyway, the thing that didn't happen prediction under your perturbation, okay? Some people quibble with the use of the word counterfactual, so we can, whatever you want to call it is fine. Anyway, the point is that if you take the difference between these 2 things, this is the image that you get out of it, okay? So there's a red blotch and a green blotch, and there's no blue blotch, okay? So where did the red blotch come from? Well, it came from the fact that there was a red blotch on the horse, and where did the green one come from? It came from the fact that there's a green blotch on the sky. And in particular, if you look at what's happened to the location of the red blotch, what you find is that tells you what the flow was on that part of the horse, okay? And of course, similarly, there was no flow, or only a little flow. The camera moved only a little bit, so there was a little flow on the background, okay? And the blue guy was occluded by the horse, so it disappeared, right? So basically what this is saying is that there's this little program, which is basically like you take the difference between the perturbed image, the intervention, and the original, and then you analyze that by basically looking at the diff, okay? And then you have an argmax on position, and that tells you flow, okay? And in particular, for those who are devotees of flow, you'll know that there's a hard problem with unsupervised flow, which is the large homogeneous objects, because basically you can't tell if something has moved. If, here's a large homogeneous object. If I put a point here and then I move, like it looks red everywhere, right? So you don't know where it's actually moved, unless what you've done, which is what's being done here, is this sort of little hypothetical counterfactual perturbation that's done to actually make it not homogeneous spatially, okay? And so it turns out that you can actually get like by far state-of-the-art results on unsupervised flow with this algorithm. Yeah.
Is this in any way related to disentangled representation?
You know, that's a good question. I don't think it's disentangled in the sense that in that literature, in that they were wanting the neurons to be disentangled. Here, I think there's a way of extracting the components that is programmable. Like, it's almost a programmable thing. Like, that's what remind me when you said programmable. Like, it's a little programmable. You can sort of set up these little programs to extract what you want in this kind of logically consistent way. But I don't think that the concepts are like represented in the neurons of the model in any kind of factored way.
What about in populations?
I kind of would doubt it, although I mean, it's a bunch of this model is a big vision transformer, so I don't know. Probably not. I don't know. Okay, so, all right, so now I'll tell you another counterfactual and then I'll wrap up. So this counterfactual is a motion counterfactual. So here's another view, here's another image from my kitchen. I'm just, literally, you just stick this image into the model trained on kinetics. That's a subset of YouTube. And so, okay, here's this image, and I want to move the box. So I move it a little bit by moving that one patch on the box. And then what you can see is that, okay, this is the counterfactual prediction. And you might not see it, but actually, like, there's a difference between the two. Basically, if you see it goes back and forth. Okay, the box has moved, right? So if you take this pair of images, this one and this one, you can put those together under the flow algorithm. Just run flow on that pair of images. That's where the box is, okay, right? And that's basically our Spelke segmentation. So what this is basically saying is just that you can get a very simple notion of Spelke segmentation out of this kind of like construction, okay? And it turns out that this is way more accurate than the version that I showed you earlier, which doesn't have the ability to make counterfactual motions and then sort of figure out what has to go with what, basically. I'll skip key points. And then I'll just describe one more prediction problem in my remaining few seconds, which is basically that you can, this original problem was basically conditioned on just pairs of frames. You can also condition this on camera motion, okay? And you can imagine this as being biological to the extent that humans have like referred copies of how they move their head, and they also have otoliths in their ear, so they know quite a bit about the, like, at least inertial version of camera motion, okay? And in fact, that's why it's so easy to build a gyroscope and stick an IMU device, inertial unit of some kind, and stick those into cameras. So actually, just as a plug on the data set, the baby view data comes with gyroscope data, so we know something about head motion with them. Anyway, the point is, you can train a model with this head motion conditioned version of the problem, and as folks in my group have found, that allows you to do like novel view synthesis, like what would happen if you moved your head, okay, in one action or another, right? And then similarly, and you can do this without any strong need for any kind of priors, but also you can get a depth out of that, because basically once you have flow due to an in-plane motion, then the inverse of that is depth, right? Which allows you to basically, you run your counterfactual, move the object in plane, not the object, the whole scene, by moving your head back and forth, essentially. That gives you a flow map, which then gives you a relative depth structure, okay? And you can do really well on unsupervised depth with that problem, okay? My point was just to tell you that for a variety of these types of intermediates, so like optical flow and like figure ground segmentation and perceptual grouping and like, basically instance segmentation, and then some other structures like depth maps, and you can generalize that to you can do 2D, 2.5D to 3D filling in. A bunch of these intermediates, maybe not all of them, but I think perhaps all of them can be constructed by basically taking a masked predictor with the right type of temporally factoring mask, and then running a little intervention program on it, running a little program, a little counterfactual. I'm going back and forth between thinking the right way to think about it is counterfactuals versus little intervention programs. Either way, the point is that like in this kind of fairly predictable way, you can take models trained this way and extract structure from them. So basically what I'm imagining, right, and this is I hope the future, is that you basically think of the system as growing with a bunch of different like computational nodes that extract things from each other. Each node arises as a little counterfactual analysis program. Of course, it would be nice if those programs could be parameterized and auto-discovered, right? As opposed to right now, what I've shown you is basically handcrafting the little programs. They're easy to write, but still we write them down by hand, right? Ideally, if it were something that could be auto-discovered, we could go from our Sutton, Efros, Spelke, Marr hypothesis to something that was kind of a synthesis with something Darwinian, right? Ideally, this would be the structure that comes out. Of course, that's far in the future. We don't have something like that. But anyway, the point is this is where we think they come from. I'm over time, so I won't tell you about the use of these models, but you can do better physics predictions if you have the intermediates and have numbers on them that look good in a table. But what I really would be curious to see is if we can make better models of the whole visual system in this kind of way. And that's a subject of ongoing collaboration with neurophysiologists. So we'll see. So I just wanted to thank the team who worked on this counterfactual world modeling and be done only 3 minutes late, so I apologize.